Hi everyone. On this part, I want to talk about the application of Reserpine that nowadays we use as a medicine for a high blood pressure treatment. It works by lowering a chemical in the nerve called norepinephrine. This helps the body to relax. So by that, the blood vessel get wider, heart slow down, blood pressure goes down. Reserpine was one of the first medicine for this, but now it not used much because it has a strong side effect, and now we have a better medicine. For the second application of Reserpine, Reserpine also used to treat mental illness in the past. So we go back to the past. In 1950 to 1970s, it was used to solve a problem like schizophrenia, mania, and agitation. It worked by reducing a brain chemical called dopamine. This helped with the symptoms, but it also caused a bad side effect like the first one. For example, it makes us feel very sad or depressed. Then it makes us shaky and stiff muscle.
Okay, for the chemical structure, Reserpine is a pure crystalline single alkaloid. It is a white to yellow powder that becomes darker when exposed to light. It is odorless, insoluble in water, slightly soluble in alcohol, and freely soluble in acetic acid. It has a chemical formula of C33H40N2O9, a molecular mass of 609 gram, and a bitter taste. Reserpine is an alkaloid found in the root of Wolffia, Serpentina, and Vomitoria. Reserpine has a complex organic molecule with several rings and various functional groups. Here is its structure. As we can observe, it has a complex pentacyclic core derived from the Yohimban skeleton. Multiple mitosis group attached to different part of the molecule, and is the linkage to a 3,4,5 trimethoxybenzoyl group, several chiral center, contributing to its specific stereochemistry. At its heart, Reserpine contains an indole nucleus. This is a bicyclic heterocycle consisting of a benzene ring fused to a pyrrole ring. Many alkaloids are derived from the tryptophan, an amino acid which naturally contains an indole moiety. This indole part is crucial for its classification as an indole alkaloid. Reserpine also follows the Yohimban alkaloid skeleton, which is a pentacyclic structure that found in many natural occurring alkaloids, most notably those derived from the Yohimbi tree. Its core structure that modified by various functional groups, including hydroxyl group, methoxy group, and ester group to form different Yohimban derivatives. The Yohimban skeleton is characterized by a 5-ring system, a carbocyclic ring formed through the C17 to C18 bond. For the classification of the compound, Reserpine belongs to the class of compound known as alkaloid, which is a natural occurring organic compound containing basic nitrogen atom, often in a heterocyclic ring, and typically possess significant physiological activity. Reserpine perfectly fits this definition. Reserpine also specifically classified as indole alkaloid. This specifies that the alkaloid contains an indole nucleus, a 6-membered carbon ring fused to a 2-benzene ring, and often include isoprenoid unit in its structure. Reserpine also classified as Yohimban alkaloid, which is a subtype of indole alkaloid characterized by the presence of the Yohimban ring system. This is a more specific chemical classification based on the core skeletal structure. The intricate structure with multiple chiral center, methoxy group, and ester linkage make Reserpine a fascinating molecule from a chemical perspective and explain its potent pharmacological action as an antihypertensive and antipsychotic agent.
Next, we go to Reserpine, building block and biosynthesis. The first building block is L-tryptophan. It is essential amino acid and the source of indole in Reserpine and the precursor of serotonin, a neurotransmitter and hormone found throughout the body. To convert tryptophan into serotonin, the body needs vitamin B6, niacin and glutathione. Niacin is also a key metabolite of tryptophan. Excess serotonin from carcinoid tumor, poor absorption in up or blood tryptophan issue may affect brain function or cause mental retardation. This issue can be overcome by supplement. The second building block is tryptamine. It is monoamide alkaloid derived from L-tryptophan and contains an indole. It is found in trace amount in the brain and may act as a neuromodulator or neurotransmitter. It is formed by decarboxylation of L-tryptophan through the enzyme aromatic amino acid decarboxylase or AAD. It is likely stored in neuronal vesicle and released during stimulation, indicating a role in neural communication. The last building block is secologanin. It is a monoterpenoid glucoside and a key intermediate in monoterpenoid indoalkaloid biosynthesis. It is produced from loganin through oxidative cleavage by secologanin synthase. It has a reactive open chain structure that enable further biosynthesis reaction. It's combined with tryptamine in a Pitted-Spranger reaction to form streptozidine. The first biosynthesis is for L-tryptophan. The phospholinopyruvate PEP and erythrose 4-phosphate is condensed to form shikimic acid through a multi-step enzymatic process. This L-tryptophan is undergo shikimic pathway. Shikimic acid is then converted into chorismic acid, which serves as a key branching point for aromatic amino acid. Antaranilate synthase catalyzes the conversion of chorismate into antaralanic acid. Antaralanic acid undergoes several transformations, including concentration with PRPP to produce indo-3-glycerol phosphate. Finally, tryptophan synthase catalyzes the conversion of indo-3-glycerol phosphate into L-tryptophan. Then, L-tryptophan is decarboxylated by the enzyme aromatic L-amino acid decarboxylase or tryptophan decarboxylase. Then, this reaction removes the carboxyl group, producing tryptamine, which contains the enduring characteristic of many bioactive alkaloid. Then, biosynthesis of secologanin. The pathway begins with GPP formed from IPP and DMAPP. GPP is converted into geraniol, which is then hydroxylated to form 10-hydroxygeraniol. Through several oxidation and cyclization steps, 10-hydroxygeraniol is converted into loganin. The enzyme secologanin synthase, a cytochrome P450 monooxygenase, catalyzes the oxidative cleavage of loganin to produce secologanin.
I'll be discussing Gilbert Stock's landmark 1956 total synthesis of Reserpine. Reserpine is an alkaloid extract from Rauwolfia serpentina, traditionally used to treat high blood pressure and mental disorders. Stock's synthesis was groundbreaking. It was among the first to demonstrate that complex natural products could be synthesized in the laboratory with precise stereochemical control. Reserpine features a pentacyclic structure with multiple stereocenters. Stock's strategy was notable for several reasons. He utilized the Pictet-Spengler reaction to form the C-ring, creating a tetrahydrobeta carboline system. He controlled stereochemistry at key positions using chiral intermediates. He employed strategic functional group transformations to assemble the complex ring system step by step. Let's delve into some mechanistic highlights. C-ring formation. The Pictet-Spengler reaction between a tryptamine derivative and an aldehyde form the tetrahydrobeta carboline core. E-ring construction. A Michael addition strategy was employed to build the E-ring, establishing additional stereocenters. Final steps. The synthesis conclude with oxidation and esterification reactions to complete the reserpine molecule. Stock's synthesis was a significant milestone in organic chemistry. It was the first to showcase how complex alkaloids could be constructed using rational design and stereochemical control. This work validates the concept of biomimetic synthesis, mimicking nature's pathway, and inspired decades of research in alkaloid and natural product chemistry.